Well, hey everybody, it's Steve, and today we're going to do a little presentation on introduction to limits and continuous functions. Basically, it's kind of Calc 1 stuff. I had to reach deep, trying to remember a lot of this stuff for limits, so it should be pretty interesting. Oh, I got some feedback there. One sec. Turn that off there. That helps. Okay. I don't know how many people will be watching this. Again, the math has been hit or miss. We've had anywhere from 20 to 40 sometimes, but I like to think that people may be interested in some of this stuff. If not, it's cool. But for those who want to have some basic introduction stuff, I think a lot of us are just trying to come in, give a basic overview of the topic, and then if people got more specific questions, they can dive a little bit deeper into it and get some of the more heavyweights, right? Because I'm not a mathematician. This is literally stuff that I am just remembering from my college days. And then I have a college book that I'm using along with other resources. This one I'm using here is actually going to be Calculus and Analytical Geometry by Sherman Stein, which actually is funny because I was the instructor for my roommate back when he was in college. That was actually his instructor, which is kind of coincidental. But anyways, I do have a midnight in here, so... Hello. Maybe between the two of us, we can kind of knock this out. And if EO wants to come in, or
he's already in here.
Oh, did EO pop in?
Yeah, EO's in here.
Let's get him shown here. Let me give you some people mods. EO.
Going.
EIO. Okay. All right.
Drake is traveling across country, right? So I don't think he'll be able to join us.
Yeah, I know. He can watch later.
Well, I wouldn't say cross the country. I think he's just
getting out of the path of the hurricane.
Yeah.
Well, let's just jump into it. Again, I am doing a very preliminary overview. This can get very, very complicated very quickly. I'm doing some simple stuff, some examples, and giving you an idea of what actually we mean by a function, what we mean by continuous function. And by the way, there is a slight difference between continuous functions and contiguous. I'm going to kind of explain the difference at some point, but continuous just means a function doesn't have any discontinuities, and a contiguous means that it's side by side. So if you have a function and there's no breaks in it on the line itself, that's called a contiguous portion of the function because there's no breaks in it whatsoever. But anyways, it's a little bit more than we need to get into. But let's actually talk about limits and what we're doing. So let me screen share and present. So if everybody in the outside chat, if you guys will let me know if you guys can see this, that would be just swell. I don't want to move that over, so let's see here. Just scroll that down.
Yeah. You might. Yeah. There we go. People can see you present it yourself.
Okay. So what do we mean by a function? What do we mean by a limit? What our limit tries to do is kind of tell us what's going to be happening at a particular point at a function, but the function may not even have something in that domain. In other words, we may not be able to stick in a number there where the function makes sense. Most of the time, that's something like division by 0. A simple function such as 1 over x, where x equals 0 is undefined, right? As you guys remember, if you divide by 0, it's no bueno. The universe explodes. Cats start mating with dogs. It's chaos everywhere, and it's not a good thing. Except in higher maths, there are some ways of doing it, but whatever. But for the most part, a function is undefined when the denominator is 0. So what a function wants to do, what a limit wants to do is tell us what's going to be happening at a particular point, even if that point doesn't exist or not. A very simple function, like the one I have here, which is 2x squared plus 1, which is what type of equation, Midnight?
Wait, which one over here? 2x squared.
Squared plus 1? What kind of function?
Excuse me. It's a parabola going up a little and then going up. No, hold on.
What do we call it though? It's not a linear, right? Because it's not in the form.
Yeah, no. It's a quadratic. It's a quadratic.
Okay. So it's quadratic function. So we know it's going to be a parabola, right? And what we want to do is find out as that variable x approaches the value of 3, what happens? What do we get? What do we arrive at? So I'm going to show you what this looks like graphed. And I love this little graphing program. It's just brilliant. So let's just pull this over here.
Yeah.
Okay.
For some reason, I can't do limits still, unless you figured out how to do it.
No, it has limitations, but for what I need it for, it's actually pretty good.
Yeah.
Again, it could be better, but eh. So what we're doing is we're seeing this parabola, right? And we already know a couple things about this parabola, right? We already know that it's offset by the origin by 1 because of the 1 there. We already know that it's a quadratic, meaning it's going to approach from this direction, from this quadrant to this one. And we want to figure out what we're doing at x approaching 3. So as x approaches 3, which is, remember, 1, 2, 3 on the x-axis, we're going to go up here. We're going to go check this out. And we're going to say, okay, what happens at 3? Oh, there you go. So at 3, what does it say the y is?
The y is 19.
Okay, 3 is 19. So as it approaches, right, from the left, which means it's from this side, from your left-hand side, as it approaches, you'll actually see the numbers on the x-axis go up, and as well as the y. And way I showed this here in this graph is if we plugged and chugged some numbers in there, let's say we put 3.1 in here, the outcome is going to be 20.22. And you could verify this if you want. And by the way, when you do this, very, very careful. When you remember the order of operations, when you stick something into this variable x. So let's say I have 3. Well, yeah, 3 there. Let's say x is 3. What do I do first? Do I do the 2 times x, or do I do the 3 with the exponent first?
You do the exponents first.
Okay. So if I put in 3 there, what do I get?
9 times 2 is 18 plus 1 is 19.
Okay, perfect. So you always do the exponent first. Make sure that you're well aware of that. If not, it'll lead you to heartache and disappointment. And again, the universe explodes. So 3.1 we try, right, which is a little bit lower than this value. It reduces this a little bit. 3.001 reduces a little bit more. You can kind of see that somewhere right here between 2.99 and 3.001, it's probably going to be about 19, right? You can kind of visually see that because as I'm approaching from the right, it's going from 17.82, 18.8, 18.9. It's probably going to be about 19.
But hold on, Steve. You're not showing the graph.
I'm not showing the graph, right?
Oh, okay.
I'm just showing the chart. I'm just showing you visually on the chart. So on the chart, it's going.
Who's David?
I don't know. Show him.
Oh, right.
Oh,
yeah, David. Sorry about that.
So
show broadcast. Here we go.
All right, so this is kind of giving us an indication what we can kind of expect to see. And then again, when we go to the graph, we can actually see that the limit is approaching 19 when I get to 3. When I actually at 3, boom, it actually is 19. So the way you can solve this one, and this is one of the easiest ways to solve it, right? Limits are not easy past this point. I can tell you right now, they're not fun. EO's going to go, oh, Steve, they're really simple. No, they suck. Okay, let it suck. Let's solve for what it is. They suck. And especially, it's not so much the limit factor. It's rearranging the equation to where you can actually be able to get an actual limit. That takes a little bit of work, and we're going to actually get into that, and I'll show you. But in this particular equation, it's very simple to figure out the limit. You literally just substitute x in for the variable. So, because I have no denominator here, I don't have to worry about it blowing up or being undefined. So if I put in 3, as you said, 3 squared equals 9, right? Times 2 is 18, right, yeah. Plus 1 is 19. Okay.
I didn't know you wanted me to answer. I was like,
that's cool. So this we know is a valid equation. We already know that this actually works. Okay, so the limit as x approaches 3 for the function 2x squared plus 1 is equal to 19. We all agree? We're on the same page?
Yes.
Awesome. And Dave, you're on the same page? EO?
Yeah.
EO hasn't slapped me yet, so that's a good sign. You there, EO?
Well, no, I am, but we should point out that if a function's continuous, then its limit at that point will be the same as the function's value. In fact, that's the definition of continuity, is that the limit as x approaches a of f of x equals f of a. So
I'm going to get to that.
You're doing great. The only thing is I would have chosen a whole to begin with where the function's value is different than the limit, but go ahead.
Okay. Yeah, I'm gonna get into that point of some
well, actually, sorry. If I have a suggestion for the next thing, you should probably tackle is actually explaining what a function is.
I could do that. I mean, well, I was going to actually do that when we start doing what's called injections, bijections, and surjections, mapping of functions to different things. I thought by now we all know what a function is.
Well, I didn't get too much into that. I can't define it off the top of my head. I need to, but
a function is basically something you put something in, you get something out.
Yeah, the function is always one-to-one.
It's one-to-one correspondence,
right? You can't have a function that you know, that has this. I think it has the same. It can't have the same x.
We'll get into that. We'll get into that. I also want to get into what's called relations. You know what a relation is? If I have like x squared plus y squared, y equal that actually is called a relation because there's not a one core.
Yeah. Well, you know,
we'll get into that another time.
Okay. I just figured I'd
it's here.
Yes.
Okay. So this equation is going to be a little bit more complicated. Okay. If f of x is the function, which again, we're just putting this equation, we're just making this part of this. This is the function. That's all it means. And I want to put in some values to kind of determine what my limit is going to be for this. Okay. So I'm going to pick something just above 1. What happens if I put 1 in this equation as x equals 1?
It'll be 0 on top and the bottom because
what happens when 0 is on the bottom?
You can't deny it. You know, a couple things, or you know, undefined, or you get infinity. You know, I've seen it called infinity.
It's not it. Okay, let's clarify that. One, the universe explodes. That's the main thing. We don't want the universe to explode. It is undefined. It is called complex infinity, but complex infinity has to do more with the North Pole of a Riemann sphere, which I'm not going to get into. EO can do that presentation because I don't want to deal with it, but he knows what I'm talking about. But when you see something like you put in Wolfram Alpha, you get 0. It'll say come up with a complex infinity. For the most part, just don't, unless you're going into more deeper maths, ignore it. It's just don't divide by 0. Okay, it's undefined in the reals for division because P over Q as the division, the ratio of integers as P over Q, is only valid when Q is not equal to 0.
Yeah, I know, but I like to, I like to go back to an earlier lesson on the Taylor series. If you see a 0 with an exclamation point, don't panic. You can divide by that.
That's fine.
Simply 1.
So Steve, here's a really good way to illustrate why we don't divide by 0.
Because God hates it.
Well, sure. Let's say I have a pie though, and there's 6 of us. I can divide it in 6 slices. I can divide it in 2 slices, etc. Right? Here's the problem with dividing anything by 0. Suppose there are 10 of us, and how many ways can we divide 0 slices of pie? The question doesn't even make sense, right? Does everyone get that? So it's meaningless, and that's the problem. We can't.
1 divided by purple. Who knows?
I can't give you 0 slices of pie, or or if I have jelly beans, if there are 100 of us and we're splitting a bag of 0 jelly beans, what does that mean even?
Right. Eric asked, no epsilon delta. Oh, I'll get into epsilon delta. I didn't want to start off with that because everybody would be already.
Wait, who's Eric? Away. Who's Eric? Bring him in.
Eric W.
If the person has even heard of the epsilon delta, Steve, you need to have him in here.
It's open to everybody. The link to join is to the Great Debate community. Just go in there and get it. Come on in.
And let me give Steve. Okay, just so it's clear, the very fact Steve is attempting this, Steve deserves kudos for. Contrary to what some people say on the internet, we're not part of Steve's fan club. I can write a book about what I don't like about Steve, but this is very brave.
You do not. What does that mean? You love me.
Are we sure about that?
Wow, I'm hurt. What was up with that?
My point is it's very brave to do what you're doing because epsilon delta is no joke. It's very rigorous. And as you saw with the proof last night, I was working night shift, actually. It's funny. It takes a little bit of ingenuity to do it. So yes, it's not easy.
Delta is not fun. In fact, that's one of the hardest things I have to do with limits, and I hated that. But when we get down to that, I wanted to be able to prove the first thing, and this wasn't part of the book. I wanted to be able to prove it, and I actually had to enlist EO's help because I was like, okay, I'm stuck at this point. And then we kind of worked it out. But anyway, good. So. Yeah, one thing, math is something that's universal. Doesn't matter what you believe. Math is math. So this applies everywhere. So, okay, back to the limits here. And by the way, thank you for that, EO. And I know you do love me. But
sorry, great point. I just saw on Twitter they discovered a cuneiform tablet that showed the Babylonians knew about trig 1,500 years before the Greeks did. And this is an important point.
Wow.
Let me get on the soapbox for a second.
Sure.
Trig is trig. And it doesn't matter what your worldview is. It doesn't matter which church you worship at. Guess what? It's the same trigonometry. And I can't hit that point enough. And that's why some of us are gravitate towards math, because it doesn't matter what your worldview is. We're going to get the same answer. Sine of 90 degrees is 1. Cosine of 90 degrees is 0. Tangent of 90 degrees is undefined. Sorry, Steve. Go ahead. I'll get off my soapbox.
And And by the way, like I said, this is one of the things I struggled with in Calc was limits, the more advanced stuff. It is not something easily to grasp.
No, not really.
It's not. So, but anyways, let's move on. So let's stick in a number here. So we're going to put in something close to 1 because again, if we put 1 in, we have 0 on the bottom. We cannot take the limit if there's 0 on the bottom. There are ways to do certain things called La Hospitals rules. We're not going to get into that. Again, that's beyond the scope of this. But what we're going to do is we're going to stick in a number here, and I'm going to show you. Okay, at x equals 0.001, and this is just the argument to this function. We're just arbitrarily setting x to this value. Okay, not a big deal. But when I do the
hold on. 1.01 cubed. Is that still 1?
No, this. I already did the math for you guys.
Midnight, if it helps, what he's doing is this function is not defined at 1. But if you notice, it's defined for every value to the left of 1 and every value to the right of 1. And so what Steve is doing is looking at values arbitrarily close to 1. Do you get that, Midnight?
Right.
Yes, I got that.
1, but either to the either side of 1, to the right.
No. See, I got that part, but you know.
1.01 squared is equal to 1.030301. Okay.
Oh, never mind. Then you got
this right here is equal to this, which is equal to this, which is approximately equal to this.
Yeah. All right. I guess. Go ahead. Sorry.
We good?
Yes.
All right. So I've already done the math for you. So and I also made a little chart. This is actually from the book. So they actually did the math. But if I pick random numbers, like I said, to the left and to the right, look what happens. At 1.1, I put it in this again. Remember that you said about a function, right? 1-to-1 correspondence. For every value I put in, I'm only allowed to get one specific number out, right? I can never get 2 values for a single input. Not good for a function. So
unless you were dealing with vectors, but that's another story. Go ahead.
No, any for a function. Vectors are a little bit different. But so I'm at 1.1, right? I'm going to get this value. At 1.01, I get this value. You can kind of see that this value is going lower and lower towards 1.5 maybe. And as it approaches from the right-hand side, right, these values start going up. And right about here where 1 should be, right, I got 0.9, 0.99, and 1.1, 0.101. Right about here where 1 is going to be, you can kind of guess it should be about 1.5. That seems about reasonable, does it not?
Yeah.
Yeah.
Oh, can you guys see my precursor? I mean, see my cursor here? Or is that too small on the outside?
No,
it's pretty small, Steve.
That's what she said. How about that? Does that make it larger? Can you see it?
Yeah.
Well,
okay,
the cursor is pretty small.
The cursor. Yeah, it's connected. It's selected this odd.
Yeah, you're just gonna have to like bear with me. I can't make the cursor much larger.
But for Midnight and David, are you guys watching? This is the important point. This function isn't defined at 1, but we can get as arbitrarily close to it from the right-hand side and the left-hand side to 1 as possible, and that's what Steve is doing. You guys see that?
That's true.
That's critical. Arbitrarily close as we want. Okay.
Right.
Now,
what happens if you set it equal to 0.5?
Well, 0.5 doesn't matter. At 0, it gets undefined. 0.5 is going to be to the right. It's going to be way down here. So it's going to be some really low value. You want to do the math, put in 0.5, cube it, -1, and then over 0.5 squared minus 1. I don't know what it comes out to be.
Hey, Steve, did you graph this function?
I do believe I have a graph, yes. Which I was going to get into.
Yeah, you can show that.
I was going to wait, but this function looks like this.
The hyper.
Okay.
That's what I thought.
So it looks like that. But before I show you on the graph, I want to wait on that. Okay.
All right.
Okay. So the way to solve this now, you have to get this in a form that you're not going to be dividing by 0. Oh, they said there's no cursor on the stream. Well, it's just you're gonna have to go bear with it. I'm gonna try to get a pad or something where maybe we can use. But so I'm gonna go down. So the way we do this is we basically remember with the binomial distribution yesterday or a couple days ago. Remember?
Yes,
okay,
if I remember correctly.
Right. These things all tie together, and one thing EO will tell you: everything you learned prior somewhere gets down the line used again. These things are integrated with each other. Okay, there's really not much standalone in math.
Yeah, I was
Okay.
just I was just gonna bring this up, like, you know, when you're doing x cubed minus 1 equals x squared plus 1 plus x plus 1 times x minus. You got it.
Right. So this is basically just reworking, and I'm not going to go through it. If you want to remember how to do this, go look at the other presentation. But this is how you rework this right here. And basically, it's just reworking it. So I have another way of expressing it, and I always group. This is how I learned it in calculus. This is how I learned it in nuke school. You group. And the reason why you group is because you can easily see that these can cancel out.
Yeah,
That's
yeah,
okay. That's
yeah,
why you want
but
to do it that way. What's
yeah,
that?
but you know, you're still left with you know, with the denominator.
Right,
You know,
but
only this time, if -1, if you put like a -1, you get, you know what I mean? Like before,
right, but
if you were to plug in one, sorry, go ahead. You
bear,
know,
bear with me. I'll get there. Bear with me, okay?
sorry, I'm just excited. I don't know.
Okay, that's good. No, excitement's good. We all get excited by math. Well, not so much. But whatever.
This is just
Yeah.
factoring out x minus
At my
1.
age, if I get excited with anything, it's good. So, okay, so I know you can't see the pointer, but if you look at the in the outside chat, if you see x squared plus 1 plus x quantity, and in the new quantity x minus 1, you see that the x minus 1s literally will be 1 over each other. So you can cross them out. So x minus 1 will cancel out on top with the x minus 1 on the bottom, leaving you with x squared plus x plus 1 over x plus 1. Right. So all I did was I did a binomial expansion. Again, if you decided to check it, you could just say x times x is x squared on the bottom. X times x is x squared plus 1 minus 1 equals 0. Then x 1 times 1 is, or 1 times -1 is -1. So x squared minus 1, when you expand it, is x plus 1 times x minus 1. Right. Okay. Go ahead. Eel.
So if I may, so you make an excellent point, but as a pre-calc teacher, I have to point out, you have to specify, you put a comma, x cannot equal 1. After you do that, now you're allowed to make it anything you want after you've done the cancellation. But before the cancellation and during the cancellation, you have to reiterate that x cannot equal
-1.
positive
Right.
1.
Well, x. Why cannot why can't x equal 1?
Well,
It's
wait,
not-
hold on. First of all, in which function, the original one or the new one?
No,
Because
in
the new one.
where, okay, see where it says x squared plus 1, quantity x minus 1, and we simplified that to get the equation x squared plus x plus 1 equals x plus 1 over x plus 1.
Yeah.
And we canceled out the quantities x minus 1. That's providing that x isn't equal to 1, as he said, which I didn't include.
Yeah, I know, but that's
why is it
Forgive me, Midnight. You need to stop focusing on x minus 1 because we're not at that neighborhood of -1. We can look at that limit later, but right now we're only, and this is an important point, Steve. We're only worried about the neighborhood around x equals 1. Do you get that, Midnight? We're only concerned about being close to x equals 1.
Right.
Nothing else matters right now to us.
Okay, so so you can see how we reduce this, right? At Midnight.
Yes.
X squared. Okay, so if we go down, we start taking the limit now. We couldn't take the limit in the form of x cubed minus 1 over x squared minus 1. Feedback. Okay.
It's not for me.
We couldn't take the limit of x cubed minus 1 over x squared minus 1 because if x approaches 1 and x equals 1, you have division by 0. Here in the new way of rewriting it, right? We basically all we did was rewrite the formula of the equation, and now if I put in 1, what happens to the denominator?
It becomes 2.
It becomes
Well,
2.
you just add it.
Okay, right? Because it's not 0, correct?
Yeah.
Okay, because again, we p over q is not defined for 0. So if we do the math now, we stick in 1 for all the x's, we end up with 1 squared plus 1, which is going to be equal to 3. 1 plus 1 on the bottom equals to 2, and we get 1.5, which if you go back here, which is about what we expected to get, right? Because if you look at the graph here, the graph, we're in the middle between 0.99 and 0.01. If you put 1 there, we would expect to be about 1.5 as it approaches from the left and from the right. And also here, I put this for, clarification purposes. If we put in 0.9, we get 1.5. We put in 1.01, we get 1.50075. We would expect 1 to be in between those. And I could have written that out as an equality, right? And how would I have written that as an equality? I would have just said 1.263 is less than 1.5, which is less than 1.5075, correct? Midnight?
Yep.
Okay, so I didn't write it as an equality, but I think you can figure out the why I wanted to show you. Look at it. We're in the kind of the neighborhood from the right. or the left, and then we're kind of in the neighborhood from the right. As it converges on the function, it should get 1.5. And now I'll actually show you the graph. If you actually go here to...
And Steve, if I can just take over for a second. On your graph,
yes,
please zoom in to x equals 1. Okay. So you're about to see, folks, the limit of technology. If a calculus student, let's say even 50 years ago we're doing this, he would put a hole where that x equals 1.
Yeah. And by the way, I'm adding it right now. But you have this program, they haven't fully, it's a newer type program. They haven't implemented this yet. They say if there's reasons, but I have to actually click it. And now I can put the hole that you're talking about.
Okay, great. So everyone's still with me? Limit. I just called a midnight limit. David,
can you see it?
David and Midnight, are you still with me?
Yes.
There is a hole.
Basically, you're still saying that you can't use that because it's still a limit. No matter how close you get to one, you still can't be one.
Right, not quite. So Steve showed, see where the hole is. The hole is at 1, 1.5 because the function is not defined there. Now, this is the beauty of what Steve is doing. Steve is showing that we do have a discontinuity here. There's a hole. Discontinuities come in 3 major flavors: holes, vertical asymptotes, and jumps. So the point, there's a hole here, but the fact that the limit exists, and Steve showed it what it was, we can fill in that hole and we can make this discontinuous function a new function, a continuous one, namely 1 plus x squared over 1 minus x. Sorry, Steve, go ahead. And by the way, this is exactly what happens when we do the derivative. We're basically filling in. It's a removable discontinuity, but that's a little bit farther than Steve probably wants to go today. But the whole point is there was a hole, and Steve filled in the hole.
Right, and that's exactly right. And so if you look here, if you look at where it says 1 undefined, the way I didn't put the newer version of the function in, but with the original, it has that hole there, and it's at 1.5 on the y-axis. Right now, he's exactly right. The discontinuities would be, and this is why it's called a discontinuity. At this point, there is a break in that function, so you cannot go, think of it as a gap, right? The other way you can have discontinuity, which you said was an asymptote, where you're approaching something, right? If I'm approaching an axis, but I never reach it.
You can't touch it, but you can never touch it.
Once you reach vertical, you can't take the derivative of a vertical. It's a 0. Oh, it's undefined. So at that point, it's a discontinuity. The other one he talked about, you said jump. So you're talking about like a Gaussian floor function?
No, I just meant, for example, we could be mean and we could have the function defined way up at top, like y equals 10.
But I mean, when you say jumps, if you do a floor function, you get jumps which have discontinuities as well.
Right, but Steve, in this context, so we could be mean. We could make this function. We could define it at x equals 1 to have the value y equals 10, and you can see that we jump all the way from where it should be at 1.5 all the way to 10. Right. Just a point, derivatives you want to talk about, Steve, we have to have that there's smooth and no cusp. But that's, again, we can do that next time if you want. We're a little bit far afield.
Okay. All right, so let's continue on.
So just one more question. So
sure, go ahead.
Basically, by redefining that function as an equivalent function, you've filled in that hole.
I've eliminated that hole, and now I can
that's beautiful.
That's exactly true.
And that's the theory behind limits, when we can save functions and make them continuous. And again, derivatives are just taking limits, and they're called, when you have a derivative, you're hoping that it's a removable discontinuity at the origin as h goes to 0. That's brilliant. Whoever that guy with the mother and the baby.
David. Exactly. And when we get into the first principle, when I do a presentation on using h going to 0, define a derivative, and actually that way is a very good way to prove the power rule, which I'll get into eventually. It's not complicated per se, but it's very intense. I actually had to do this in calculus, but way back when, and it takes a lot of, we had to actually do this in pen, right? So it takes a lot of scratch work. But it's a very good way to prove the power rule. So I kind of wanted to go back to first principle at some time, right? We're not doing first principles in this hangout. Abay's asking in the live chat, no. But at some point, yes, we're going to be talking about that because I think it's important.
Yeah, but I'd ask you what first principle is, but you don't want to get into it, so we'll just wait till we actually get there.
Yeah, well, basically what we're talking about is the very first ways of getting a derivative by h approaching 0, where you have a function of x, f of x plus h plus f of x divided by h.
No, f of x plus h minus f of x divided by h. The limit is h equals 0.
Yeah. Okay. So I would say I have to remember it myself. I haven't used it in a while. Okay, so moving on. This particular function. Now, what do you think this kind of function would kind of look like? We have an absolute value of x. These are absolute bars, and that just means you always have a positive value. So it's x over the absolute value of x, where x is always going to be, when you evaluate this, you're always going to get a positive result. Okay, so if I put 0 in there, it's still undefined. Would you agree?
Yes.
Because it doesn't matter. It's still absolute value of 0 is still 0, right? So universe explodes. Now, if I put a value in for like 3, well, 3 over absolute value of 3, which is 3 positive or 3 positive, I get 1, right? If I put -3, it's -3 over -3, which is absolute value of -3, which is
+3.
+3. So -3 over 3 gives me a -1. So I can kind of gauge that at f equals 0 when I have an undefined value there. But if I put any positive number in, I get 1. If I put any negative number in, I get -1. So I can basically write it as an equality, and I can say, or inequality, and say if f of x is greater than 0, I'm going to end up with 1. If I say it's less than 0, it's going to be -1. Okay.
Can I say what's happening?
Yeah. Well, yep. And I'm sure the graph while you're doing that. Go for it.
The limit is undefined.
Well, hang on. Let's see here. Actually, where did I? Here we go. So this is what it's going to be looking like. Okay, this is kind of a weird looking function, but it's not really. It's what it's actually doing. It's just saying as I'm approaching from the left, which is from the negative infinity, which is to the left side of the screen, as I'm coming towards the origin, right? I'm coming toward a limit, right? Which in this case is going to be 1. It's undefined, right? Because if I is this the right thing? Yeah, did I get this right?
So if I may, Steve, you might want to talk
right.
about right-hand and left-hand limits.
That's not the
The
right
fact they don't agree here, that's probably the way you want to.
That's not the right one.
Yeah, no, it wasn't the right one. I was wondering.
Yeah,
No,
no, that's right. I was just say, hang on, I got this. No, I'm going to left and right limits here in a second after this, but I need to get this right. So x divided by ABS. I didn't. That's not even what it should look like. Divide.
It should be -1 until the origin, Steve, and a hole at the origin. It should be +1 from the right and a hole at the origin, and a hole at +1, and a hole at -1. 0 minus 1. So the problem here is this is the kind of jump to cut. Well, we can't save this function because there's no limit because the right-hand, left-hand limits don't agree.
I like how you say that we can't save this function. It's not salvageable. So I will get it. I'll show it.
Steve, you need to. There's some there. It's showing there was a subscript.
I don't know how to write this function here. X.
Don't
You
you
had
already
it,
have
buddy. I
that
don't know what
function
happened.
up there?
That first second.
Oh, I already have it. I knew I have it somewhere.
Up
You
there.
had it. You showed it to us.
There we go. Okay.
There it is.
Here we go. This is the function. Okay, this makes a little more sense here. Okay, because I'm actually approaching 0. I want the. This is where I should have the problem right there. Okay, so 0 is undefined because obviously it's 0. We have it in the denominator, so that makes a lot more sense. Okay, and up here we have as it approaches from the right, it's also undefined as well. Okay, so you got that right. So any positive value for x, right, which is going to be to the right of the origin, is going to give me a +1, which is this value of y right here. Any value that's to the left of the origin is going to give me a negative value of y, which is going to be 1, -1. So down here. So is this. We can say that we can take the limit as it approaches 0, right, for this function, if and only if a is not 0. Okay. If a is not 0, right, then we can actually take the limit as x approaches some value, some arbitrary value. We're going to call that a. Okay. Now this is where it gets a little much, a little confusing, but the value we want for a is some value that's not 0 in this particular case, that we can take a limit from the right-hand side or the left-hand side, and then we can compare them and see if there's an existence of a limit for both sides. Okay. So the definition of a limit is literally this formula here. As x approaches a, the limit of the function of f of x is equal to L. So as x is approaching some arbitrary value, the limit of that function is defined to be L, which is the limit. So the best way to think of this is very simple. Look at the limit of the function, which is going to be this f of x right here, as it goes to L, right? As x approaches a. So you basically have two things happening. You have x going to a value, which is the x on your Cartesian coordinate system, right? As that approaches some arbitrary value, the function, the original function you have, is going to go to some limit. That's all it's kind of saying. So when you break this down from the right and left, the way we write this is this negative sign or plus sign here. If I say the limit as x is approaching 0, minus is always from the
Right.
The right. Okay. So as x approaches 0 from, no, actually to the left.
That's from left. Yeah. So the
Yeah.
negative.
Negative to the left. Yeah. Think about it, because you're coming from negative infinity, right? That's coming from the left-hand side of the Cartesian system. So negative. So as you approach 0 from the left, right, the left-hand limit, it's going to be equal to -1, which you've already seen up here, right? We already determined that anything you put in here that's negative is going to be -1, right? So as it approaches from the left, from the negative infinity towards the origin, it's going to be -1. Now, as the other side, which is going to be approaching from the right, which is going to be the plus here, it's going to be 1, because any value you stick in for x from positive infinity towards the origin from the right is going to be equal to 1. We good on this so far, right?
Yes.
Yeah.
Okay, so far so good. This is not that bad right now. Now, if and only if, and you have to remember this because this is going to be critical, if and only if there is a limit that exists, but for both the right-hand side limit for the x to the a plus and to the left x to the a minus, and they are equal, then we can say that the limit of x towards a exists. Okay, so let's repeat that. If you find the limit from the right-hand side, if you find the limit from the left-hand side, if they both exist and they're equal, then the limit as to x goes to a exists. Okay, that makes sense?
Yes.
And that doesn't always happen.
That's the case here, isn't it?
Well, you know what? Here, let me show you here. You get another screen out here.
Well, I mean, I kind of said that before, but I'll let Steve explain it. Why that's the case.
Go to Wolfram Alpha here because we love Wolfram Alpha. Let me take the limits. Can you guys see this in Wolfram Alpha?
A little zooming in would be.
Okay. Well, I could try. Here we go. That better?
Yes.
Yep.
Okay. Let me make sure. Let me try to get this in here right. So before I do anything else.
So, if I may, fellas,
How do you put that in there? Limit x. Why is this not coming out right?
As x approaches, I think you're gonna put limit x as x approaches.
No, it's the input's right, but it's not the way I had it earlier. It showed something different. I was trying to get it.
Steve, if I may.
Oh, I did it. So anyways, go ahead. Sorry.
A really cool way to think about continuity is that small changes in x mean small changes in y. Can all of you see what happens in this function as we go close to 0? All of a sudden, we jump up +1, and there's no way that we can salvage that and make this a continuous function. Continuity just means no breaks. That's a useful way of thinking of something.
Okay, this is what I put.
There's no breaks in the graph.
Yeah.
All of you get that?
Yep.
Yes.
And this is what I put. Actually, this is because I worked on this earlier. If you look closely, the limit from the left, right, is -1, and the limit from the right is 1, but these are not equal to each other, right? -1 is not equal to 1, correct?
Correct.
True.
So there's no limit at. So there's no limit at a there. At that point is 0. The limit does not exist, and we say the two-sided limit does not exist. This is what E was saying. This is non-salvageable.
Yeah,
You cannot
I also
rework this to get anything.
Yeah, I also said that before, maybe prematurely, because I've studied some of this stuff before. So you forgive me if.
No, that's cool. You got it. You got it. So EO, so you want to expand that real quick? It's just that I want to make sure people realize that it was an if and only if. Just because I got a limit to the left and I got a limit to the right, they weren't equal. They have to be equal for that limit to exist at A.
So the limit of a function basically means what is the function's behavior near this point. And the sad fact is, well, we can't even talk. We can talk about the function's behavior as we approach from the right here in this example, as we approach from the left. But there is no behavior as the function approaches because it depends on which direction you're coming, from the left to the right. And in this case, there is no limit because you guys can see that just intuitively. Like, what should the limit should it be? -1 or should it be +1? We can't decide, right? There, and so
right.
I want to make the point. Does anyone notice that when we're dealing with the real line, there are only 2 directions to approach a number, right? Can all of you see that from the left to the right? Everyone with me?
Yep.
Yes.
Mm-hmm.
Imagine now in vector calculus, imagine if now we're talking about 3 dimensions. How many different ways would there be to approach a point? Does everyone see there be infinitely many ways?
Yeah.
Hold on a second. Hold on. If it's 3 dimensions, wouldn't there be only 3 ways?
No,
No, because you have multiple vectors in those 3-dimensional space pointing to one point.
Because all I have to do to change direction is move point.
Well, okay, yeah, right.
Point something in another coordinate system.
Don't worry. The point I'm trying to make you appreciate, it's not quite as hard as I'm making out to, but you can appreciate how simple it is just to have 2 directions. Does everyone understand that, as opposed to infinitely many?
Right. Yeah, infinity throws you for a loop.
And as Eulogy points out in the live chat, in order to be differentiable, you have to have a continuous function. If you were to try to do a derivative of a non-continuous function, you get undefined. You can't. If I put 0 in here, right? I'm going to have undefined in the denominator. You can't take a derivative of that.
So if I may, Steve, I finally get Eulogy back. Continuity is sufficient. I mean, it is a necessary condition, but not sufficient. You need much more, Eulogy. You need something, in layman's terms, you need a smooth curve. So in other words, they can't be sharp corners, they can't be cusps. So again, continuity is a necessary condition, but not a sufficient one for differentiability.
So yeah, so let me put that in layman's speak. It could be continuous, but that doesn't necessarily mean that you still can differentiate it.
Right. All Ferraris are cars, but not all cars are Ferraris. Ferraris are the differentiable functions of the Ferraris of cars.
There you go. And if we want to get into like smooth functions and all that other stuff later on, that's going to be beyond the scope that I would ever get into. But I understand the concepts. But if you want to do one on manifolds, that'd be great too, on 3-dimensional manifolds and smooth 3-dimensional functions, like for planes and undulating and all that cool topological shit. That'd be great, but
you and Han should get together and do Einstein's field equation. I'm telling you, Steve.
I've tried to. I literally have asked him like for months now. So okay, but let's move on. Let's stay back to functions. So Midnight. So what are the 2 conditions in order to make sure that you can say that there's a function at A as x approaches A? What are the 2 conditions?
They both have to. The limit has to be equal on both sides.
The limit has to exist on both sides and has to be equal. Correct. Okay. So here's some additional rules of limits. Okay. I didn't include all of them. These are not this is non-exhaustive. This is a non-exhaustive list. So don't think there's not a lot more rules. There are, but some of the more basic ones. One of the more common ones which you'll be using is the limit of a constant equals a constant as x approaches A. You also can see this as C. Lim C equals C. This right here, and I think let me give you an example. It's very common. So let me blow this up so you guys can see this. Okay, so if I take the limit from x to 2, if x equals 2, right? Oh wait, that's not the right one. Wrong one. Well, you know what? I can change it. That's okay. I got so many different things. So let's take a constant. So let's pick a constant. Okay, any constant. Come on, why do you gotta compute so much? This is not what I wanted. Oh, I see. I put it in the wrong place. We'll just put limit 3 for x. X to 3. Here's how you write it on here. You know what? I don't use Wolfram that often. You use Wolfram more. There we go. That's how you write it. Okay. So in that particular case, I'm taking the limit of a constant. 3 is a constant, right? It doesn't really matter what I'm putting here. If I put x goes to whatever, there's nothing in there that changes, right? So the limit of a constant is always the constant. Would you agree? Because I can put anything. If x goes to 0, who cares? It's still 3, right?
Yep.
Okay, so the limit of a constant is always a constant. Another good rule to know is that if you have the limit of a constant as a product times the function, right? K times the function, you can actually just bring the K out. Okay, so I'm left with k times the product of the limit of the function, which is a very handy thing to know when you start using these things to manipulate things, right? So if I have the limit of the function, right, and I have a k as a multiplier of it, because that's all I'm doing, I'm just multiplying the function, I can actually take that k out of that part of the equation, and then you could use it to do some cancellations and manipulations, okay?
So
Kind
Steve,
of make sense?
just inside baseball for your benefit, you can see why, just epsilon over k. So if epsilon works, then epsilon over k will work. That's just for you, Steve.
Okay. The next one, the limit of x as approaches x, this one is also used quite frequently. This is actually just saying, and you know what, there's cheat sheets for this. Don't expect to memorize these until you've actually done a lot of calc, but there are cheat sheets to this, but at some point you are forced to memorize these. But
the limit of the sum is the sum of the limits. Yeah, that's
yeah, that's a fun one. So x is not that complicated, really, and I'll explain that one next. But the limit of x equals a, as x approaches a is always going to be the limit there. So if I have like lim x equals, just say, okay, let's say I have lim x equals. If x is approaching 5, what is the limit?
5.
5, because you take 5, you put it in for a, you get x approaches 5 equals 5. So that's all you're doing. So basically, as x approaches a, the limit of x is going to be equal to a, which is going to be the same as L. Okay. Now, this one looks a lot more complicated, and it's really not. This is where it's kind of deceiving because it's really simple, okay, but it looks complicated. The g of x right here is just another function, right? I'm already be using f of x for functions, right? And that function is, if I say f of x equals x squared, all I'm doing is I'm making something where I can stick in different values for x and get something out with a one-to-one correspondence. So I'm just creating another function, and instead of calling it fx2 or fx something else and get confused, we just decided to call it g of x. We can also call it h of x and other things you'll see, but these are just two different functions. Now, if I want to take the function as x, the limit of x going to a for these functions, and I have it in this form, it is exactly the same as taking the limit of one function, taking the limit to the other function, and adding them together. That's all it's saying. So it's basically the limit of the sum is the sum of its limits. That's a fancy way of saying that. Okay, you find it used very often when you get into using calc with more than one function like this. The other one's very, very similar. This is the one, the limit of a product is the product of the limits. Midnight, if I want to take the limit of x approaching a for the product, which means multiplication times, of the function f of x times g of x, do you see I can just separate it out and say, okay, that's got to be equal to the limit of the function f of x times the limit of g of x, right? Same thing as the sum of the sums. It's just instead of having an addition sign there, I'm actually having a multiplicative operation or multiplication sign. Say that 10 times fast.
Multiplicative.
Multiplicative, yeah.
Well, I mean, Steve, you know, just to say, you know, if
as x goes to a, yeah. Mm-hmm.
Yeah, if f of x is equals x, so that's 5, and g of x that's equals x squared, okay, yeah, and they have the same limit, it would be 125.
Well, think about, yeah. Well, I'm not gonna do it in my head, but I do keep it simple. Look at, just plug in something like x, just x itself, right? Don't even have to worry about taking it squared or anything. F of x is just x, right? So if I have the 5, if x equals 5, right?
Yes. Okay.
So in this particular case, the limit of 5 is 5, and the limit of the g of x is 5. So the product is 5 times 5 is 25. So I can say the limit of 25 as x approaches a is the same as the limit of a constant, right?
Yeah, but Steve, aren't, you know, isn't there a rule of two functions being the same?
No. What do you mean?
Well, I mean, you know, if never mind. Go ahead.
Okay, so look, if I just put 5 into x here, 5 times 5, because I end up with the f of x equals 5, g of x equals 5, right? So 5 times 5 is 25. The limit of 25 is 25. Here I'm going to do the same thing. The limit of 5 is 5 times the limit of 5 is 5, 25. Either way, all this is going to equal to 25. That's, you want to make sure that you get the same result, right?
So Steve,
both of these things are basically just a restatement of the commutative and distributive properties of addition and multiplication.
Because they hold true. Because they hold true.
So hold on.
Because they do hold true.
Yeah, let me shed some light. What Steve is doing is building a powerful toolkit, and this is important. When Steve and I were discussing this last night a little bit. Mathematicians, contrary to popular opinion, don't like getting their hands dirty. So we make all these fancy rules. And so what Steve is doing is building this huge toolkit so he can approach every function possible that's whether it's continuous, whether the limit exists. So again, Steve is building up this wonderful toolkit, and hopefully he'll get to the point where the limit of the composition is the composition of the limit with continuous functions. But go ahead, Steve.
Yeah, I'm not getting into compositional functions at this particular hangout. At some point, we probably have to do composite functions. Not one of my favorite things to do, but I can do composite functions. But the key thing with this, and as Eo points out, is that once you have the toolkit here, you don't actually have to kind of go through the steps. If I see an equation that has the limit of x approaching a, and I have two functions that I'm taking a limit of the product, I can just go ahead and do it. I can just apply the rule. You don't have to show the minutia at that point if you get the rules right. Okay. So it is a toolkit, and it is a time-saving factor. Just like the power rule, right? When you have the power rule and you're using a derivative, you don't have to derive the power rule every time to use it, right? Because excuse me, I'm sorry. I'm telling you, it's a pain to derive it. We're going to be doing that eventually. You don't want to go through those steps. So these are things that in your toolkits that you can use to help your life when you're doing limits. So the next one would obviously we have to worry about what happens when we have a quotient. Okay, so in this particular quotient, the limit as x approaches n for the ratio or the quotient of the function f of x over g of x is the same as saying if I took the limit of the denominator here of f of x over the denominator, the limit as x approaches a of g of x. Now, because I'm dealing with the denominator here, I have to add the caveat that g of x cannot equal 0, right? Because if g of x equals 0, what's the limit of 0? The universe explodes because the limit of 0 is 0. So this has to be included in this quotient rule for limits. It's required. Yeah. Okay. But the way this comes in handy is because if I have an equation in this form, I could set it up and just say, okay, I want to take the limit on the top. I want to take the limit across the bottom and see what I get. And there are other ways of manipulating too. For example, you can always rewrite a quotient in the form of an inverse, right? In the inverse way, which is writing it as a product, right? Remember, division is the reciprocal function of multiplication, and multiplication is the reciprocal function of division. So there are ways of rewriting these things that way as well. Now,
so you should point out you used this rule already in one of your proofs earlier. The earlier example, executed.
I did, but I indirectly. But yeah, I did. Yes, you're exactly right. Go ahead. While you're doing that, I'll show you where I used it.
Yeah, and so the point is,
right
he's already tacitly used that rule, and you can already see midnight where it came up, right?
Yep.
Because right here, I took the limit across the top. I took the limit across the bottom. Right. That's exactly the same way as just taking the limit of this whole function. So in this particular, this 1 squared plus 1 plus 1 over 1 plus 1. That's exactly when you would use this. Exactly. But I tacitly used it. Right. I didn't have to invoke it and show it and all this other thing. I just used it. But you're exactly right. So let's continue on. Now we're going to try some problems. Yeah, because people ask me, hey, Steve, why don't you include some practice problems? Well, here's the part of the video.
I'm the one who said that.
I think it was you. Okay. So I took I do take things on board. If you guys ever watch this video afterwards, or somebody who watches this video afterwards, if you don't want the answers, do the problem, stop the video, and go from there, right? But let's actually try to do some sample problems. So first sample problem. You guys get your pen and paper out? Practice problems. Let's do number 1.
Hang on.
Good selection, Steve. Number 3, the algebra will be involved for some of the people in the chat.
Okay.
I took a good random sampling. These are practice problems out of the book. I took a random sampling of the ones that I knew how to do pretty easily. I wanted to keep it pretty simple. So, but I thought.
Steve. Actually, you know what? To keep it so people, I'll write the answer I get in the side chat. I suppose I could. I don't know. How would you?
Midnight,
let me open up the side chat.
Midnight, do you have only one lung?
No. Why?
You always sound so out of breath.
Well, I'm overweight, and I seem to have nerve damage. So I don't know.
Oh, I'm sorry, buddy. I'm
Do
sorry.
you vape?
That backfired.
No, I don't vape.
You know what? When I quit smoking, I didn't even vape. I've never tried vaping, so I'm kind of glad I didn't, because I know a lot of people kind of like it, but I don't want to get. I got to give up smoke, so I don't want to go like vape. You know.
Okay, so if I just plug it in, it'd be...
All right, so
one question, real quick. I'm wondering, do you guys? I'm not sure if it's even being covered in this one, but did you cover what is it? Limits when it's applied to functions with removable discontinuities?
That was Steve's second example.
When the second one that we did, we rearranged the formula where we could get rid of the discontinuity to rewrite it in a way which is to rewrite it in a way where you don't have that discontinuity anymore. We have removed that discontinuity in that way. That's exactly what I did in the second problem.
And in fact, spoiler alert, 2 and 3 have removable discontinuities of x equals 2 and x equals 1 respectively. Spoiler alert.
All right, so let's not jump ahead too much. This is the first problem. This is exactly like the first problem we did. Okay, it's pretty straightforward because, again, we're not worried about a denominator. We're not worried about it blowing up. So we're asking what happens with the limit as x approaches 5. So what can I do to solve this problem?
Well, if you want me to just tell you, you could just plug the 5 in.
Okay.
Just like that, then you get.
Let me scroll down here to the answers.
Okay, 12.
So I want to set it up of x approaching 5. X plus 7 is equal to L, right? Because it's going to be in that. I'm doing it a little more proper. This is the official way of doing it. So I just stick it in there and I get 12, right? Because 5 plus 7 equals 12, right? The limit approaches as 5 approaches. You know, this actually should be underneath here, but whatever. But these are not multiplied. This is x approaching 5 is equal to 12. You're exactly right. Okay, so let's go to the next one.
And hold on, Steve, if I may, I'll just say that all those rules you laid out, number 1 uses 2 of the rules, namely that the limit of the sum is the sum of the limits, and the limit of a constant function is the constant itself, and the limit of as x approaches 5 of x is 5. So yeah, there were 3 or 4 things going on, but as you pointed out, it's very simple to see the limit is 12.
Yeah, exactly. Some of these you kind of intuitively use the rules, right? So now the next one's a little bit more difficult, right?
Can I actually do this one?
Yes.
Okay. Well,
we'll start off with this. What a value in here are we trying to avoid?
We're trying to avoid a equals 2.
A equals 2, right? Because at that point the universe explodes and we all die. Not Steve, a good thing.
Anyway, moving on. If you just plug a, you're left with a squared minus 4 over a minus 2. However, if you want to avoid that, a x squared minus 4 is x plus 2 times x minus 2 over x.
Great job, Nick. Sorry, I was applauding you. Sorry.
Oh, I was applauding. Okay.
I was like, what? But yeah, the x minus 2 cancel out, and you're left with a plus 2. Similar thing for number 3.
All right, so let's look what you did there. So we're gonna go the way I already did all the answers. So I want to take, I'm gonna put this under here so you can't read ahead here. Okay, so exactly right. What I did was, you take the binomial expansion, right? So I'm expanding this out, which we learned the other day, right? We know that x squared minus 4 is going to be equal to.
I'm sorry, Steve. It's not a binomial. It's a difference of squares. It's called a difference of squares.
You're right. Okay, it's difference. Okay, you're correct. It's a difference of squares. You guys remember back in the day, you had to learn to do what's called completing the square, that kind of stuff. Yeah. So, all right. So you're basically. You're taking this and you're factoring it out. You're creating 2 quantities. And then what we can do is we just take x minus 2, cancel that out with the x minus 2 on the bottom. And what are we left with? X plus 2, right? Well, this is simple at this point. We just stick in 2, right?
And you get 4.
Yep.
All right. And we know that when we know by the rules, this is supposed to be a capital L, but whatever.
I'm currently doing number 3.
Okay. Hold on, fellas. This is beautiful. Again, there should have been a comma. X cannot equal 2. Sorry, go ahead.
Yeah. Okay, so at this point, we just have a limit of 4, the constant, and then it's limit of 4. So the answer to this right here is 4. Okay?
Yep.
We got it. Okay.
Number 2.
Excuse me. Moving on to 3.
3. Yeah, I'm doing 3 right now.
right? 3 is as x approaches 1, x to the 4th minus 1 over x cubed minus 1. Now this one, again, you have to do factoring. You want to be able to.
Yeah, it's a little involved with this one.
It's a little bit involved. You want to be able to eliminate something on the bottom so you don't have that potential for division by 0. Okay, so we'll step through it as you're doing it. So 3 is coming up here. Here we go, 3. So if you don't want to look, don't look. But the rest people, this is how it's factored out. And again, if you want to double check it with Wolfram, go ahead. But this is basically, again, I'm getting quantities that I could put together that equal to x to the 4th minus 1, where I can start doing cancellations.
Oh, see, this is beautiful. I can see us doing partial fractions in integration using these same techniques of factoring. Like I said, if your audience is interested in this stuff, we could go forever with these lectures.
Well, I mean, it's math. I mean, you spend forever. I mean, it's just one thing leads to another, right? And again, all these concepts are integrated with each other. There's not much standalone stuff in math.
Stephen, let me elaborate on your point. I was told, and I believe it after teaching calculus, the main reason students struggle in calculus is not because of limits necessarily, but it's because they don't have the trig down and the algebra down. And if you have the trig and algebra down, you typically find that students excel at calculus. So you're exactly right. You have to integrate everything and synthesize everything you've learned up to this point.
I had algebra obviously going into the Navy, but I got to tell you, it wasn't until military school where you learn math in ways you've never learned. I mean, you actually learn a lot better, I think, of how to manipulate these things and how to rearrange them. Because I guarantee it, I would have not have been able to do this in junior high, even though I took algebra. We were taking pre-algebra in junior high. There's no way. I didn't know how to do it very well, so I sucked at it. But anyways, so we have these quantities out, and you can look away. Okay, so what we do is we're going to be canceling out. We're going to be canceling out the quantity x minus 1 by the quantity x minus 1 on the bottom. And again, I wish I could have a way to show you that these is. I just line them out. Just you take them and you cross them right out. And I'm left with the quantity x squared plus 1 times the quantity x plus 1 divided by x squared plus x plus 1. Now, again, if you need to work on the algebra to manipulate these, we can do another hangout for that. I'm going through this pretty quickly. I'm not showing you the algebra because that's going to be a lot more involved than I kind of wanted to get to. But you can tell what we're trying to do here, right, people?
Yes.
Okay.
And now that you have x squared plus 1 over x squared plus x plus 1, it will be easier to find the limit.
Right, because I can just stick in 1.
Negative. Yeah.
Okay, so I stick in 1. Boom, I get 1 squared plus 1 plus 1 plus times 1 plus 1. I end up with 4 on the top and 3 on the bottom. And the limit of a constant is the constant. So my limit as x approaches 1 is 3 over 4 is equal to 3 over 4. Boom. There you go.
You meant to say 4 over 3. Steve, do you want to scroll up for a second and go to the original function? I want to show them something.
And by the way, real quick, if I may, I know, and AO, you may disagree with me on this, but this is how we learned it. When you're in grade school, they always say, never leave an improper fraction with the numerator higher. Later on, they don't give a fuck. Okay? Just seriously, straight up, people. It doesn't matter. It doesn't matter. This is perfectly fine.
No, had you written 8 over 6, I'd have an objection, but 4 over 3 is just fine.
It's reduced.
Can you scroll up for a second? I want to show
yeah, you always want to reduce it, but just because the numerator higher.
Okay, I got the answer for number 4, which, I mean...
Hang on, buddy. I want to show you guys something cool. Look at that.
Okay.
See the x to the 4th minus 1 and the x cubed minus 1?
Yeah.
See the exponents, everybody?
You notice something here?
See, Andreas, you guys see that? You see the first one's 4 and the second one's 3? Steve made reference to L'Hopital earlier, and you'll learn later on you could simply just take the derivative 4x cubed over 3x squared, and then cancel out the x's, and then that 4 over 3, where does that come from? It comes from the exponents there. I won't make it a hard and fast rule. I just think it's a really key.
And also, there's also ways of figuring out. Okay, this is good. I didn't want to get into this, but I knew he was going to be here.
Well,
so
too bad, Steve.
Figured. But there are also ways of figuring out limits by if you know the coefficients of the highest derivative of the polynomial.
Yep, and the powers, yeah.
And the powers. Yeah. So, but that's beyond the scope of this particular introduction. So EO and I really have to have a chat one day. I want to pick his brain. It's funny. Like I said, I know what he was talking about, but it's just like I don't even want to bother with that stuff. So, but yeah, but there are ways. I told you there's many different ways of finding out limits. This is just an introductory, but yeah, eventually you learn ways of taking you find the highest power, the highest order, and then you can use that to find the coefficients and blah blah blah, and it sucks. But anyways, let's go on the next one. The next problem here is number 4. So as x approaches 3, 1 over x plus 2.
Yeah, you just plug in the 3, you get 1 over 5. That limit is easy. You just plug in the 3. Good.
All right.
And x cannot equal -2, obviously.
Correct, because then I have 0. So you just plug in 3 here because I can't blow it up.
No, at Midnight, you're right, but so how do I put this? This is actually kind of an important point. Midnight, you're right to be worried, but you're being a little bit fastidious.
I won't get offended.
You don't have to worry because we're nowhere near -2. Do you understand, buddy?
Right. We don't care about -2.
Yeah, I know. I just don't know. I just feel like adding that in. You always tell Steve that comma x not equal.
Not quite the same thing. So it's like the singularity of a black. It's like the event horizon of a black hole. We're nowhere near the event horizon, so we don't need to worry about it. Does that make sense?
So I understand what you're saying, but conceptually you're a little bit off because again, we don't care what's happening at x -2. This hasn't.
We care about what x happens at x equals 3.
Right. That's what we're taking the limit.
Yeah.
Okay. Right. Okay. So you're right, but you just plug in 3, you get one limit of 1 over 5, which is a constant, which is 1 over 5. Okay. Perfect. Now let's go to the next one. Oops, I just showed. So the limit. This one's easy. I mean, how simple is this one?
Limit is 25.
The limit's 25. Boom. Done. That's it.
Okay,
That's all you gotta do.
Okay. Number 6.
Why is this true though? Why is it the limit of 25 as x approaches 3? Why is it 25?
Because it's always 25. It's 25.
Because it's a constant. The limit of a constant is a constant. Right. That's it. Boom. Okay. So the next one.
You go down a little bit for number 6.
Okay. So we're gonna be taking this one apart. This one again. We're approaching from the right hand side, right? Because it's x approaching 1 plus. Okay. So you have to keep that in mind. But let me. I think I actually mapped this one. So
Steve, may I just say the reason why this is a difficult problem is that the absolute value function is something called a piecewise function. It's in pieces, and since it's in pieces, we're going to have right and left hand limits. Does that make sense, everybody?
Yeah. I always had a problem with piecewise functions. Still do.
This is a little more difficult one. This is not an easy one. I didn't graph this one, but that's okay.
Well, this is the same. It's the same one as the one without the -1s.
Well, let's check out what's going on here. So let's do it for this first step, okay? So we say that as the limit of x approaches 1 from the right, because we're finding the right-hand limit, right? We can actually start plugging in numbers here, and this is the only way to really kind of to think about this is as I'm approaching from that right-hand side, we can kind of see if we plugged in the numbers, it's approaching the number 1 on the y-axis. Okay, so if you put in 6, it's approaching 1. If you put in 4, it's approaching 1. Anything you're putting in there, it's starting to approach the number 1. Okay, and actually I did graph this one, so let me kind of show you. This is one of those ones you kind of have to like graph out. And by the way, there are graphical ways of doing these things as well, but graphically this isn't the right one.
Number 3, third line. There you go.
Okay, so thank you, because I knew I had it in here somewhere. So as I'm approaching from the right-hand side, right, it is approaching this value here. And what happens at 1?
It's undefined.
It's undefined because 1 minus 1 is 0. Absolute value is 0. So we can kind of see as any number for x I put in here, boom, doesn't matter. 1, I get 1, right? Any one. Okay, so because what happens is any number I put in, did I not solve that one? No, I didn't. I just, well, that's the answer. But the only way to really do it is again visually, because as I'm approaching this way, any value that I put in there, if I put 6, I'm literally 6 over 6 is 1, right? 10 over 10 is 1. So any value I put in there. So in this one, you're just going to have to graphically do it, and say, look as I'm approaching x from the right hand side. If you look at the graph, it equals 1. That's how you kind of have to solve this one, unless Ian knows a different way.
Yeah, there is a different way. You just use the fact that the absolute value of x minus 1 equals x minus 1 for x greater than or equal to 1, or equals 1 minus x for x less than or equal to 1. But it's just a simple algebraic manipulation. But you conveyed the point adequately, so you can move on.
Okay. The next one, this one's a bonus. I actually wanted to include this bonus one. This one is a little bit more challenging. Okay.
I'm doing it now.
Let me see. Did I graph this one too? I did graph this one. Okay. That's this graph. That's the graph here. And by the way, if you notice here, this particular program doesn't have a way to put a square root in. I don't think. At least I couldn't figure it out. So do you see how I put a square root in there?
No, hold on. You know, you can.
Fractional.
Well,
actually, look at my x. Do you notice something with the x?
Yes, I noticed that.
Okay,
but
so
but
the exponent.
If you write the word, if you write the word SQRT, that that's actually one way of doing a square root.
Right, but I don't think it worked in this Demos program. It works in math.
No, it does. It does. I've tried it before.
Okay, and whatever. It's still good practice. You shouldn't get so used to like we working. So we working with the symbols or with a function. Like square root is a function, right? It's called the square root function. You should actually know all the different ways of writing stuff. So if I write x to the 1/2, that is exactly the same way as writing square root of x.
That's true, and you know, and that works for any NF power, any NF roots. Sorry, I'm misspeaking here.
The reason that works is because the denominator here is what we're kind of looking at, which means I am taking I'm taking the square root of x to the first. That's kind of the way you look at this. X to the 1, and then it's just 2 as the denominator. I'm taking the square root of it. Okay, so there's different ways of I don't know, memorizing that, but if you just remember 1 over 1/2 is square root. What happens if I have 1 over 3? What am I taking? What root?
The cube root.
The cube root, exactly. So, and what happens if I have like just say 2 over 3? That's a good one.
The square of the cube root.
Taking this cube root of the square.
Same thing. You're both right.
Yeah, I guess so. You say it a little bit differently, but you're taking the cube root of the square, right? So I don't know. Do you guys want to do? I don't want to do exponents one of these days. I don't like these, but maybe once somebody else will. But yeah, those are good rules to memorize. So, anyways, in this particular function, you'll see that it's approaching something, right? It's approaching here.
So, Steve, if I may, this is a great example where we have a right-hand limit, and we can still have continuity if the function is not defined past a certain point. So as long as the function is defined and the right-hand limit exists, then we say the function is continuous there. So here's a case where the right-hand limit is the limit. Depending on where did you stop the function? Yeah. So this is actually a weird one, guys, because the domain of the square root function is only all real numbers greater than or equal to 0. Therefore, the entire graph is restricted to that. This is kind of a tricky example because of that.
Yeah, remember that the domain is what we're going to put in. The range is where we get out. So the domain here is literally what he says. It's all positive numbers. It's all x is going to be to the right of 0, right?
Okay, Steve, I think I got the bonus one. If
type it in there, and then we'll work it out. Okay. Okay. So the way you want to simplify this gets into another way to simplify. This is why I included this bonus one. I actually found it somewhere else, and I thought it was really good because this is another way to get to change a equation in order to actually be able to work with it. So the way we're going to do this one, we're going to do something called complex conjugate. What I call complex conjugate manipulation. Okay, manipulation by complex conjugate.
There you go. That's what I got in the side chat. If you want to quick, I probably wrote it wrong, but that's what I got.
You look at it.
Sorry, Steve. You mean radical conjugates? There's no complex numbers here, and it's
radical complex. Yeah, radical.
And by the way, it's just a difference in squares. Notice that again. Another difference in squares in the bottom.
Yeah, you're right. It's a radical. It's a radical conjugate. It's not a complex conjugate, but well, actually, you know what? These are complex numbers. All real numbers are complex numbers.
Sure, if you want.
Okay, I don't want to. Yeah, no. Okay, we're getting pedantic here. By the way, I just want to know. I showed that to Midnight the other day. I asked him to go find out why all real numbers are complex numbers, and he did, and he did a brilliant job on it. So he got it spot on correct.
Yeah, could you mind? I probably got it wrong because I rushed because I'm trying to get the right answer, but at the side.
All right, well, let's check this out. So what I'm going to do is I am basically going to times it by something, which is 1, only rewritten in a different way. 2x, it should be 2 plus square root of x over 2 plus the square root of x is 1, right? I'm just timesing this by 1 is really what I'm doing. But by doing this, I can cancel out some things because when you do a product like this, I basically just timesing the top by the top and the bottom by the bottom. So I end up with this. So basically I say 2 times 2 is 2 squared. Then I go 2 times 2 radical x minus 2 radical x, which cancel out. And then I have radical x, which is radical x squared, right? Now remember, this unitary operator here, don't forget it, okay? Because this is 2 minus, right, something. So you can't forget this little minus side. It'll kill you every time. So I'm ending up with 2 squared minus radical x squared. And there's actually another way to memorize this. Basically, it's basically like, I think it's a minus b times a plus b equals a squared minus b squared. Remember correctly?
Right, that's called the difference of squares. Yeah.
The difference of squares. Okay, so I don't think I included in there, but I did want to point that out. These are little tricks you pick up after a while, right? So, anyways, I just the bottom I don't even have to do that with. I can just take the product of 4 minus x times the product of 2 plus the square root of x, right? So I'm ending up at the top, right? I'm going to simplify this, right? Which 2 squared is 4.
Okay,
and what happens when
I did was wrong, but same idea.
What happens when you square a square root? What happens? They go away. It cancels each other out. So I'm just left with x. Now, if you notice, I could take 4 minus x and cancel it with 4 minus x at the bottom. Boom, gone.
Yeah, just ignore the answer in the side chat. I was pushing a little bit, so I got it wrong.
So what am I left with in the top?
A 1.
A 1. Never forget that.
Plus square root of x.
Well, it's not 0, people.
That's true.
A lot of people make that mistake. It is not 0. Just because I'm canceling this out here, right? This 4 minus x over 4 minus x is equal to 1. That's why you can cancel this out.
So, Steve, I hate to be the Grinch that stole Christmas, but you did a lot of extra heavy lifting here. Scroll back up to the top.
Oh, I know I did. I broke this. I broke this.
You did the equivalent of walking when you could have taken a cab. So just go back to the top. So, sorry, Steve.
Yeah.
See where you have 2 minus root x and then 4 minus x in the bottom?
Where?
At the very beginning. Okay. You should have just written 4 minus x equals 2 plus root x, 2 minus root x, and canceled there, and you're done. One step.
Right. No, I know. Yeah, but I wanted to show exactly why this works. I broke it down each step by step. And by the way, this is actually from another source, right?
That's fine. It's extra work, and again, it's not. I'm just telling you, you did a whole bunch of extra work for nothing. You should have just broken it down at the beginning. It's not.
But I wanted to show why it worked.
A lot of people coming in.
This is how it was shown in the example.
That's fine. So,
and I liked it that way because it actually shows each step. But you're right. There are simple. Eventually you'll find tricks and shortcuts in order to do this stuff, right?
Yeah.
Okay. So, anyways. What you're left with is 1 over this. Okay, so you can actually take the limit there, right? Because as x approaches 4, right, you just put 4 in there. The square root of 4 is 2,
plus
right?
2
So I'm left with
4.
Right, so I'm left with, as x approaches 4, 1 plus 2 plus 2, limit of 1/4 is equal to 1/4. So I can say that the limit of this equation is equal to 1/4.
Right, and it's important to remember that technically the square root gives 2 answers, but when we're considering this problem, we're only considering the principal square root.
Correct. Which is always positive. George is saying I can't cancel those out. I don't know why he's saying that. There's nothing I've done anything wrong. This is actually, like I said, verbatim from online calc notes.
Right, but those are written by humans, Steve. That's not. I mean, that's equivalent of saying because someone said it, I showed you a faster way. Just because someone else said it, I showed you a very.
What am I missing here? And what's
you
not
did a
able
whole
to
bunch of extra work. No, I understand the principle.
I get that. But where's the math wrong?
I didn't say the math was wrong, but I just said.
Yeah, but George is. He said you can't cancel those out.
I want to actually point out there is a typo here.
Where?
At the denominator, shouldn't it be 2 minus root x rather than 4 minus x?
4 minus x, 4x. No.
No, but he's multiplying and dividing by the same quantity, but he's doing extra work. He should have just factored the new denominator in the first step.
Right. Yeah, I thought he was doing a difference of squares at the bottom as well.
No, that's what he should have done, but he did a whole bunch of extra work.
Yeah, I see what you're saying. You're right. There is extra work put in this, but it gets the right answer. Okay. The answer is correct. It is negative.
But Steve, I love you, but that's the same as saying you were in a hurry and you took a bike instead of a cab. It's no more elegant what you did. In fact, it's clumsy. I'm just saying. I got to stand up for what's right.
Fair enough. Do you want to rewrite it and I'll put it in there so you have a more elegant way of writing it?
To be fair to Steve, everyone who's listening, I'm not trying to be hard on Steve, but this technique that Steve used is the technique used for a lot of limits involving radicals. And that's the same trick. You multiply
This is the reason I did it the way. This is how I learned to do it.
Oh yeah, me too. Yeah,
no, it's not like it's like completely hosed. This is how I learned to do it. So I mean, there are more elegant ways of doing it, but I think the reason this way I showed it and the way I learned how to do it is because it shows each step and what we're doing to get to get something we can actually get the limit of, right?
All right, so let me extend all around to Steve. It is a common technique in mathematics to multiply by 1 in any form you want.
Right.
And that's what he did there.
Right.
And to add 0 in any form you want.
Not the most elegant way of doing it. I will grant that. Okay, not the most elegant way. And so there are but I said from the beginning, there's multiple different ways of doing this. Okay, so can we move on to the next thing then?
Yep.
Because everybody's been asking for this. Okay, so this is where all life breaks down, and we basically lose our mind. Okay.
Steve, some of us have already lost our minds, so I don't think that's possible.
So in this particular thing, let me move this over here. Oh, we do got some more people in here. So this is what people have been asking for. This is the formal definition of a limit using the epsilon delta. Okay. Basically, the way this works is, I'm going to read this. It says, given for any epsilon greater than 0, there is a delta greater than 0, so that the absolute value of the function minus the limit is less than epsilon when 0 is less than the absolute value of the parenthetical group x minus a is less than delta. Wow. Yeah, really convoluted. Yeah. Okay.
Can I help, Steve?
Sure.
So what that means.
By the way, I added your inequalities here just because you sent these to me, so I added these in for. But
it's fine. So basically, what it's saying, folks, is you can make the function arbitrarily close to the limit simply by making the value of x arbitrarily close to the value. So small changes in x mean small changes in y. Just a minor typo this year. You meant to say that a less than b implies a squared is less than b squared on that in those parentheses.
A is right here.
Yeah.
Oh, well, you remember what I said? It's not a typo. I just said it wrong. Okay. This one, I actually didn't find it. I didn't find this out there. So I actually tried to do this one myself by proving very informally, very ineloquently. But I tried to prove that the one equation we have at the top is equal to 19. I actually added EO help between, he sent me his proof, and between his and mine, I was able to do it as well. I did it in a little different way than you, EO. So you're not going to find this very elegant, but it is the way It is the way like Math is Fun does it. I used their approach only with this particular problem. Okay.
Yeah, I've used Math is Fun too.
Okay. So let's see if it makes sense. Okay, EO. So what I'm saying is, as x approaches a, which we know is 3, the limit is 19. Okay, right. So yes. This part of this advanced formal definition, right? This absolute value here, we have to say is less than epsilon, right? We're saying that this is less than epsilon. So if I put the function in for here, which is this, right, minus the limit, I'm just substituting at this point. This is the function 2x squared plus 1 here, f of x, and minus the limit. I'm just substituting that in. It needs to be less than epsilon. What we're trying to do is basically find any value for epsilon that we can get where we can get the delta greater than 0, correct?
That's true. And here
so we're trying to find an epsilon that exists, right? That's basically, if we know we can get that value, we know that this is true. And you can use it by a bunch of inequalities. The way EO did it, he used a lot of inequalities, but it's same principle. So I'm just trying to satisfy that formal definition. Okay, so I'm taking this very first part, right? And I want to find what epsilon is, okay? Because I don't know what epsilon is. Right? I got to find an epsilon. I got to make sure it's greater than 0. Now, how do we do that? Well, again, I'm putting in the function. I'm minusing the limit next less than 0 or less than epsilon. We just combine terms, right? And follow. You following along with me? Make sure this.
I should keep quiet because you've kind of got things
Okay.
bungled. You let epsilon be greater than 0, and you find delta. So epsilon is arbitrary, Steve. I think you mean to say you have to find.
No,
delta.
no. I'm actually finding an epsilon that would work.
No, that's not how it works for every. You have to.
This is how Math is Fun does it, and I'm using their approach. They actually find a value. They say try to find a value for E that you can work with, and then stick it in to see if it works. I am trying to find that value for E.
But Steve, the whole point of limits is it has to work for every epsilon greater than delta. Epsilon greater than 0.
Well, this, like I said, this is their approach. I'm just doing it that way. Let's just go through it and to see if it works out at first. Okay. So I'm combining terms. I bring out the 2, right? I'm just factoring out the 2, right? Then I'm factoring out the exponent. Okay, right?
Yep.
So at this point, I'm just I want to get this isolated. I want to get epsilon in a value I can get. So what I did, divide each side by 2 and take basically the square root. So the square root will cancel out this exponent. You're left with the square root of epsilon over 2. This is the same value you got, by the way, EO, right?
Right, but you're taking a whole bunch of liberties. It's not true that if a squared is less than b squared, that a is less than b. Take, for example, -5 is less than 3, but -5 squared is greater than 3 squared. But go ahead.
All right. Well, like I said, let's just try this approach because this is the approach Math is Fun. And I haven't done epsilon delta in 25 years, so bear with me here. But let's assume that delta is equal to the square root of epsilon over 2, which we found here. Okay. If that's the case, I can go back and I want to find this part right here, right? X is less, or excuse me, 0 is less than the quantity of x minus a is less than delta. I want this inequality. Okay. So I just substitute square root of e over 2 as delta, right? And then I can take the square of both sides. It cancels out the square root. I can factor this down, right? I distribute the exponent. And by the way, just a distribution of an exponent over subtraction, it's just you take 2 over times x, or excuse me, 2 raised to x raised to the second, 3 raised to the second, so I'm left with x squared minus 9, right? Then I take 2 on both sides and times it. This cancels out the 2 on the right-hand side. I'm left with 2 on the left-hand side, and I'm left with 2. I distribute it over, so 2x squared minus 18. I'm left with 2x squared minus 1 plus 19, which is another way of showing this. So I'm showing this right here, which is my original thing here, right? 2x squared plus 1 equals 19. I'm taking this part right here. This is what I'm getting when I take f of x minus L. Okay. So when I'm showing for the inequalities.
No, I'm the only one confused. I'm the only one confused as to how you factored x squared minus 9 into x minus 3 quantity squared.
Where?
Go up a little more.
Yeah, I'm a little bit confused by that too.
Okay, where?
Keep going up.
Again, this one I was trying working out with EO because again,
right
this is completely from scratch.
Steve, that squared does not go into x squared minus 9. There's middle terms in there. It's x squared minus what is that? 6x minus 9.
Yeah, you're right. But yeah, you have to use inequalities to make this work. And by the way, Steve, just if you look forward, you were arguing vehemently, but you actually showed what I said. You chose delta. The whole way this works is you let epsilon be greater than 0, then you choose a delta, which is a function of epsilon, which is what your proof shows. And again, epsilon can be arbitrary. The point is you have to choose a delta that works based on that epsilon, which lower on you did. You chose the same delta.
I chose the same one, right? Okay.
Right. You kind of, there's a lot of, it's funny because you skipped a lot of steps that, anyway, I'll let it go.
There's a more elegant way to do it. If you I'll tell you what, let's go back to the definition. If you want to, I have your proof, by the way. Do you want to show your proof?
You could screenshot it and then all the steps are filled in there. They're not going to get it anyway. Abid might, but the rest won't.
Yeah, I mean, it's like I said, the delta epsilon method sucks. I haven't done it in many, many years. Don't take this is not part of my presentation. I didn't even want to add this until actually people had said, why don't you show the delta epsilon? Because I suck at delta epsilon. I will always suck at delta epsilon. So
can you just
Steve, they wanted to torture you.
Do you still have that? Do you have the screenshot I sent you of the?
Yeah, I'm just trying to get it. One sec.
Now, again, what Steve's showing you is actually part of advanced calculus, the delta epsilon proof. They used to make kids like do their best in calculus, but hardly anyone teaches that anymore. They just kind of say this is the foundation, and it's pretty rigorous. That's why I was surprised Steve was trying to. It's
very rigorous. And again, I haven't touched this shit in ages. So this is a very, very rigorous way of doing it, which is out my area. So this is what this is. I'll take the A for effort. I think I got the concepts. Trust me. It's just the it's very, very rigorous, and we have people in here that actually teaches math.
Abid, can you check my proof? See if you follow it. Abid,
and they're very, very rigorous people. So this is beyond the scope of an introduction. This is advanced, rigorous calculus stuff. So bear with us, guys. So okay, this is the prelim that you took for all of x is greater than or equal to x. Okay, right?
So for every positive, and again, we're just dealing with neighborhoods here. Go ahead.
Okay, so you're saying that the function minus the limit, and you put this in exactly that I did, right? You got 2x squared minus 18. You factored out the 2. And you're saying that's less than or equal to 2 absolute value x minus 3 squared, which is actually I think what I got, isn't it? Didn't I not get that?
That extra part in the middle there. It's
right here.
Between x minus 9.
This is he got the see he's using inequalities, right? But I got the same I got the same math, so let's just find out where he went. So he's saying now that let's see for
second line there, that's the extra step that you're missing.
Where?
Yeah, it doesn't seem like it's being factored correctly.
Yeah, no, that's not that's an inequality, not an equality sign there. That's why, because he's taken out the 2 middle terms in there, and that's why you can actually write that inequality.
You guys can see this proof that EO did, right? Is that what you're looking at? Okay, so you're saying on his proof he's missing something?
No, you're missing that second step that he's written.
That's fine. Okay, so his step. Okay, so he's got.
It's the one that has a star on it.
Yeah, the verify using inequalities.
Yeah, that is correct. What he's written there is correct. As long as if you go up the top, there, just scroll up his picture a little bit. You have that for all x is greater than 0. Right.
Okay.
You have to have that condition, or else that inequality will not hold true.
Right. Okay. We're following. Okay. So once he's at that part, right? He's going to let epsilon be greater than 0, right? Because the definition for the epsilon delta epsilon has to be greater than 0, right? Now, why did you? I got the same thing here, but why did you choose square root epsilon over 2 for delta?
Because I work backwards. I started with the limit and work backwards. That's what we all do. But then we make it nice and elegant at the end. But that's why I included the prelims. That kind of shows you what I'm doing up there.
So you kind of you just did it in your head, and then you end up with delta.
No, not in my head. I worked it out. There's a fair bit of work, and there's a lot of algebra that kind of some of the steps you skip. But so let epsilon be greater than 0. Choose delta equal to square root over 2 epsilon over 2. Then if x minus 3 is less than delta, so look carefully. Abid, I'm curious if you agree with my logic there.
Sense, but it's not expanded out. That's why it might get confusing. Because you're missing your inside, you didn't show that that negative 6x term and
that's easy. Start off with biconditional inequality. Start off with the absolute value of x squared minus 9, which is the same as x minus x squared plus 9. Is greater than or equal to x squared minus 6 plus 9. If and only if 2x squared is greater than or equal to minus 6x plus the 9's cancel. If and only if 2x squared plus 6x is greater than or equal to 0. If and only if x squared plus 3x is greater than or equal to 0. If and only if x times x plus 3 is greater than or equal to 0. And that's clearly true for all real numbers.
That's a lot of if and only ifs.
But that's how you do it.
Yeah, well, we are going so far off the path of introduction to limits. This is like major.
Yeah, this is why
Right,
they're not teaching it.
How many viewers have we lost? How many viewers?
I'll tell you what. This is why I hate the epsilon delta method. It is convoluted. It what you learn it and you get it, and then you never have to ever touch it.
See, can I point out in calc books, they always use linear functions for these proofs because anything above cubic or more, there are always these ad hoc ugly proofs. I was lucky because it's a quadratic. I could use a difference in squares trick. But the point is, this is the whole point you made earlier. The reason we have all these rules that you spelled out for everybody is because we want to avoid this because the proofs get ugly quick.
Yeah. Oh yeah. Yeah. So I mean, I'm going to close this. If you still looking at it? Do you need it for anything? Okay. So so let's forget about that proof part because, like I said, I probably did butcher it a little bit. And again, epsilon delta. Now but everybody in the live chat can see. Even people that teach us stuff, it's not easy. Okay. So all you need to know for the formal definition is for the epsilon delta is this basically this. This is and why it works that way we can get into more if he wants to have a hangout, but I want to kind of back away for that because my presentation ended with the bonus thing here. Okay, the other part was just forget about it because I not going to do epsilon delta. So anyways though, you guys kind of get the basics of the how the functions work and what we're trying to do and how we're trying to actually show what happens as something approaches something. Right? Yes. Hey George. Hi buddy.
Hi there. One of the other proofs is the triangle inequality.
We can't really.
I'm breaking up?
Yeah.
Yeah.
I don't know why. Huh.
Try again.
Okay.
Though. Try again.
I say no. One of the other tricks, or one of the common tricks that you use in a lot of these proofs, is the triangle inequality when doing these sorts of things. But you know, with the epsilon delta proofs, basically all you're doing is you're just saying, all right, I want to get arbitrarily close to the limit point. So I pick an epsilon. Now can I find an interval on the domain, the delta, in which it will be finite?
I'll tell you, George, I have used the triangle inequality when it came to Cauchy sequences. I will kill myself if I ever have to do it again.
Yeah.
Just after
anyway, what I was trying to point out,
whoever invented that shit needs to just die.
Yeah.
Because it is barbarically torturous.
What I was trying to point out to you on that last limit that you were doing, where you canceled out the factors where x goes to 4, strictly speaking, that's an illegal operation because you can't cancel out factors where they become 0. I mean that cancellation.
Well, you can as long as you note on there where x doesn't equal 0. X doesn't equal whatever the value is, right?
Yeah.
You note on there, which I think didn't EO you pointed out initially.
Yes,
right?
but that's your limit point. Usually, the way you solve those types of things is using L'Hopital's rule, where you take the derivative of the denominator and the numerator, and then find the new limit. See if you can find the limit. If it still becomes 0 over 0 or infinity over infinity, then you keep taking derivatives of the numerator and denominator separately until you get a limit.
There you go. So I think we've confused everybody enough with the whole. Once we get into the delta epsilon stuff, it's not easy, guys. And these triangle inequalities and stuff, they're not easy. And Cauchy sequences, not easy. The other one type of what's called Dedekind cuts or Dedekind. Right. Dedekind. Yeah, however you pronounce his name. Yeah, they're not easy stuff. I'm not a fan of that. I would never be able to do a presentation on that because it's beyond my level. That requires pretty heavy understanding of this stuff. But like I said, limits aren't that bad. Once you get an understanding of limits, I wanted to do a basic presentation on it. I think that I've accomplished that. The end part, just don't worry about it. It got way out of control because that is a really, really rigorous way of defining limits by formal definitions. But you guys got any question on the actual just basic stuff?
RSC227 says you're as confusing as a G-Man sermon.
Wow,
yeah. You know what? Let's have G-Man try to come in and explain some of this stuff.
Oh no! Hold on, Steve. We need to get. Excuse me. We need to get the guy who got a B+ in calculus to come in here and try to talk to us about it.
Who is that? Ronnie?
Well, no, I was thinking of somebody else.
Wait, Ronnie said he got the B. I thought he said he got an A.
Yeah, he got an A. That's right. Yeah, Ronnie said he got an A, and he also said he dropped out of college first couple days because it was too easy for bio.
That begs the question: how the hell did he get an A?
Edgar, but Yeah,
That's exactly. I don't know. We haven't quite figured that out. We've asked the same question.
Steve,
I mean,
Yeah, George.
you know, if you really want to make this whole thing about limits productive, the way I would recommend you approaching it is when you're looking at limits, is you're implying that, like in the case of series, that they converge, and why not just deal with infinite series and look at various techniques for determining whether or not a series convergence, like
We can have
test, ratio test, interval test, and all these different things. And that's a lot more interesting way of approaching things.
We could have a hangout on that. If that requires a little bit in depth that I could probably jump into, but I wanted to get some basic stuff down first. I mean, if we wanted to go into how to do infinite sequences and limit of a sequence, and how to do, you know, if we want to go into I hate his name, L'Hopital. His rules. I mean, remember the squeeze theorem, right? We want to get into the squeeze theorem. Anything like that, we could probably get into. But until I think we get some of the more basic stuff down, like I had with the order of operations, I had with the well, Taylor series isn't basic, but I want to do more of the basic presentations, just so everybody kind of gets up to speed a little bit before we start going into some of the more advanced stuff. Because that's why I didn't do the matrix one yet, because I was like, why bother do matrix if we haven't even got over linear equations yet, right? It makes no sense. So yeah, there's a lot of stuff we can get into that, sure. I actually happen to like sequences and summations and all that stuff. I find them be quite interesting, but they're not something that I think people can jump into pretty quickly. Do you, George?
I think you go in a lot quicker to that than talking about limit points and Cauchy limits and Cauchy sequences and delta epsilon proofs.
Well, that's why I didn't want to go into delta epsilon. I was talked into it. Okay, I did not want to touch that with a 10-foot pole. Now you know why.
Yeah, I mean, delta epsilon, I just leave that for a formal course in calculus.
I agree with you. See that, EO? See,
I didn't wait.
I didn't say it with you.
I was against this too, Steve. I was wondering why you're doing it. I didn't encourage you to do this.
Okay. Fair enough. Other people were asking about it before when I said I was going to do it. Anyways, so what's some of the other things you wanted for other people to do as well? If you guys in the live chat, you know, people watching, what's some other presentations on some basic math or some math you want to learn about? I'm not doing Hamiltonian operators. No, I'm not doing multivariable. No. You want to do like maybe first order linear equations?
You need to actually get an introductory course in calculus first of all. I mean,
that's what I'm thinking.
Even more basic, as in you really need to get first principles down pat.
All right. Well, I'll tell you what. The next one I'll do is I'll work on first principles and I'll also work on deriving the power rule, because I think that proof is actually a good way to show how some of this stuff actually works. Would you agree? You know the proof for deriving the power rule? You don't have to memorize, but
yeah, I do. You just need to find the theorem.
Yeah, exactly. And I have the proof for it, and I can go over that.
Didn't you kind of do that already?
No,
you touched on it a bit. I mean,
I have not really touched on it at all.
On the first one, I think it was, you had to use that kind of what was it? I call it combination notation, but like I think you guys call it choose notation.
Yeah, and they're in the live. What kind of notation?
Combination notation.
Oh yeah. That was when EO was showing a combination notation.
Yeah, combinations. Yeah. Same thing. Yeah.
And by the way, it's a Lorentz, Barney. It's not Lawrence. It's Lorentz transformation. I've done Lorentz transformations. Again, nothing I've done for too long for me to ever bother with. That's something I would actually recommend George. If George wants to explain Fourier transformations, Lorentz transformations, or anything like that, that's much more something that he or you would be capable of doing. You don't want to learn Lorentz transformations from me, trust me.
Why would you want to go into transform theory if
I wouldn't
trying to get people? I mean, you really have to gone through
a lot.
A whole year of calculus before you can really start understanding.
Well, I'm just saying that's what they're saying in the live chat, right? And I'm like, that's way more advanced than we'll ever get into right now. But I'm just saying, I asked for basic stuff, and they're giving like Lorentz and Hamiltonians and Dell and Nambla and whatever the hell. It's like, no.
Well, Hamiltonians aren't basic stuff. I mean, you're getting into some pretty advanced concepts when you start talking about Hamiltonians and Green's functions and all this.
I thought we could do basic matrix, right? That would be not that difficult. Just like Kramer's rule, how to determine it, you get a determinant, how to do an inverse matrix.
Well, it's better if you're going to try to invert matrices. Kramer's rule, remember, only holds for a 3x3 or a 2x2. Anything greater than that, you have to use cofactors.
Sure, but for figuring out a 2x2 using Kramer's rule is pretty simple to use.
That's right. Yeah.
Sure. I do remember that. So, I mean, that's something I could do a presentation on, but I'm just asking the other people, maybe, like I said, what do they want? I know Midnight wanted to do something on explaining a little bit about sets, irrational numbers, rational numbers, integers, whole numbers, real numbers, complex numbers. I thought that'd be cool.
Yeah, I sent you the presentation in DMs. I don't know if you looked at it.
You know, if you really want to do something interesting, I'd highly recommend, if you're comfortable with complex numbers, just showing that you can integrate just about any elementary function by expressing them in terms of complex exponentials. Everything's an exponential. Functions, hyperbolics, they can all be written as exponentials, and exponentials are very easy to integrate and differentiate. So when you start getting pretty complicated integrands, like trying to integrate, say, e to the x times sine x, in the standard ways that undergraduates learn that by doing various substitutions, it gets fairly involved and complicated, but it's
we haven't touched on it though. We haven't even gone to integrands yet. We barely started. We were just talking about differentials,
or even to differentiate.
Bit, yeah,
you know, like you express sines, trig functions in terms of complex exponentials. That finding derivatives of them is quite trivial.
And people are asking, they say, how about some algebra stuff? How to do algebra? Okay. Again, we kind of like skipped a lot of things because a lot of people were like, yeah, we don't want algebra stuff. We want to learn a little bit about calc, and that's why we were like doing these types of presentations. If you want to backtrack a little bit and start a little bit more from algebra or basic number theory, that's fine with me. I mean, you guys could do any presentation you want, right? I'm only trying to do presentations of stuff that I'm at least familiar enough with to be able to explain. Limits are not that hard. But when you start getting into like the advanced stuff, like the delta, epsilon delta, forget it. I'm like, there's no freaking way. I barely remember it myself, right?
He was great up to then, Steve. You should truncate it right at the end of that last example. It was good.
No, I'm going to include it all. My faux pas are everybody's fun, you know? So it's okay. I tried, though. I at least gave it a shot, right?
He was a valiant. You were close. I mean, you missed a few of the steps, but it's fine.
But dude, I tell you, for not doing a epsilon delta literally in 30 years or some shit like that, I think I did okay.
Fair enough, yeah.
I'll tell you what, if G-Man wants to come and explain to us epsilon delta, I'll be happy to listen.
He's a little busy at the moment, I think, right?
Yeah, since he's became a Jehovah's Witness, he's been really busy with them.
What?
Got to get a plug-in for my video.
That was fantastic. You know, if he's going to build you a straw man, then you need to build him one.
Did you like that, Dave? I did. Do you think he's going to understand the point behind that? No.
No, he's just going to accuse you of lying, even though he doesn't understand the relevance.
Pretty rave reviews on that video so far. So, and I thought it was funny. So I like it. Did anybody else not watch it? Anybody watch it? Did you?
Not yet.
I know you watched it. Oh. So, anyways, if people don't know what we're talking about, go to my actual main channel, Steve McRae. And I have a video out that basically I strawman the hell out of G-Man because that's what he's been doing to me. And no citation needed or no citation required. That's the new meme. But anyways, guys, I'm going to end this because we got other stuff to do tonight. Just to let you know, we have guess who coming in tonight on this channel. You want to take a guess? I'll give you a hint. His first name starts with RN and his second name ends in raw.
Really? I can't pronounce his name. Sorry, but I know who you're talking about.
Aaron Raw. Yeah, he'll be here tonight. I think at 6 o'clock, and he'll be having a discussion with General Han Solo with Richard moderating. That's gonna be awesome. And then tomorrow, he's actually gonna be on my main channel, Steve McRae, and he's gonna be.
Wait, do you mean 6 o'clock your time?
Pacific time.
9 o'clock. Yeah, 9 o'clock. Because it's already 6:26
9 o'clock
over here.
Eastern.
So yeah.
9 o'clock Eastern, and
Steve-
he's wait on one sec. He's going to be with the Atheist Edge. You know him, really nice guy that has dropped in. So it's going to be Aaron Raw and Atheist Edge taking on any kind of theist that wants to come in and give him a challenge. So, anyways, go ahead.
I was just going to say, could you please congratulate him on the success of his? Well, I wanted to ask. I'm assuming his audiobook is doing well, and could you tell him that we hope that he publishes more books? He's a great writer. He's a great speaker.
We've all told him that. Yep. Yeah. And like I said, I'll eventually open it up a little bit more. So maybe, people can come in and have a conversation with them. They're really looking for theists that wants to engage. I've been actively trying to find some, but it's been a little bit difficult. But anyways, it's time to end this, guys. So I want to thank you all for watching this. Again, don't worry about the end so much. I don't get bogged down on that, because that epsilon delta stuff, you're never going to really have to know too much about it unless you get into some really kind of rigorous formal math. Excuse me, it's good to know because it is the formal definition, but the concepts I want people to learn was just basically what's a limit, how to approach a limit to determine whether we can find the limit from the right-hand side, the left-hand side, if they're equal, and the limit exists at A. That's it. So we got the basics. If anybody got questions on it, they can message me, and if we want to do more about that. And also, yeah, we do need somebody to do trig. Thank you in the live feed there. Somebody's putting some trig stuff. I understand trig, obviously, but it sucks. So if somebody wants to do a presentation on trig, take it away, guys. Trust me, we would love to have something, not just on cosine, sine, tangent stuff, but I mean on the inverse, the arctangent, the hyperbolic functions. I think that's something that I would love to participate and hang out in that particular one if somebody does a presentation on that.
I could do that for you sometime if you want.
I would love that. I would love that. Yeah, I've seen your. If you guys don't know George, throw out your channel, because you have some amazing videos where you go on a blackboard and you're doing the whole MIT type thing in detail to solving these things and showing, why the Earth isn't flat. So, want to throw your channel out there real quick?
Don't put him on the spot, Steve.
No, you don't advertise your channel?
Not really.
Okay, no problem. No, it's okay. That's fair enough.
Here's a link to one of the videos.
But George knows what he's talking about when it comes to math and engineering. So let's just put it that way. And he does a very elegant job.
He went to MIT?
No, MIT like.
Oh.
It's basically...
No, I went to Michigan Technological University in Colorado State.
Have you ever seen a professor when they have like multiple blackboards or whiteboards and they're just writing on it, and basically it just that's his style, right? And I've had to actually do stuff like that on a blackboard more than one occasion in training and in instructing when I was in nuke school and actually in the fleet. It's a lot of effort. There's a lot of preparation that goes into that stuff.
Yeah.
So, but anyway, guys, let's end it. Sorry, Pseudo, you popped in just at the end. Did you watch? Nope, guess not. All right, guys, thanks a lot for watching, and we'll see you later.